All right, this is Calculus 1, Lesson 6. Are there any questions before we start today's lesson, either about material we covered last week or any of the homework problems? No? Everybody's okay? Okay, well, so lesson 6 is on infinite limits and asymptotes. So a lot of what we're doing, you can see very nicely in Maple. Maybe I'll switch to Maple at some point. But a nice example is f of x equals 3 over x minus 2. So this is only defined where the denominator is not 0. That means for x different from 2. And if you were to graph this function, this is the line x equal 2, this vertical line. And as you go out to infinity, this function is going to 0. As you approach 2 from the right, you're going to plus infinity. As you approach 2 from the left, you're going to minus infinity. And the notation we use to denote this is that the limit of f of x as x approaches 2 from the right, the plus sign is plus infinity. And the limit of f of x, I could either write f of x or I could write down the function, it doesn't matter. As x approaches 2 from the negative side, from the left, not from the right, this is equal to minus infinity. So there's a very precise definition of what it means for a function to have limit plus or minus infinity as you approach some point C on the x-axis. So there are really 3 things that need to be defined. One is, so this is one situation. The other situation, another very nice example, is the case where the graph of your function looks like this. In this case, this is, let's say, x equals c. In this case, for this function, this is the graph of some function y equals f of x, a different function. The limit of f of x as x approaches this number c from the positive side or from the negative side is equal to infinity. So here, the limit of this function as x approaches c is infinity. Here, there is no limit as x approaches 2. There's a one limit on the right side. There's a right side, one-sided limit, and a different limit from the left. So these are the 3 kinds of infinite limits you can have. You can have the whole function goes to infinity, or it could be a picture like this, where the whole function as x goes to some number c is minus infinity. Or you could have different limits from the right and the left. And the careful statement of what it means for a function to have a limit infinity as x approaches some number c is the following. So we say that the limit of f of x as x approaches the number c is infinity if for every m bigger than 0, there exists a delta greater than 0 such that if x minus c in absolute value is less than delta and greater than 0, then f of x is bigger than m. So what does this condition mean? Here you have c, here you have c plus delta, here you have c minus delta. And if you look at all the x's in this open interval, except at c, you never evaluate the function at c. But for all of these x's, given m, there's this positive delta, such that for every x in this interval, f of x is bigger than m. And there's an analogous definition for what it means for the function to have a limit minus infinity and from the right and from the left. But the most important thing is to have a good understanding of geometrically what this means. So the book gives a number of examples. This is example 1. We have two functions. One is f of x equals 1 over x minus 1 squared. And the other is the function f of x equals minus 1 over x minus 1. And we want to find the limits as x approaches 1 for these functions. Now, for the function x minus 1 squared, this is the line x equal 1. The function is not defined there. This is only defined for x not equal to 1. And as you approach 1 from either side, this is 1 over a square is positive, and the square is going to 0, so this is going to plus infinity. So for this function, the limit of f of x as x approaches 1 is infinity. This situation is different. Again, this is only defined for x not equal to 1. And if this is the line x equal 1, what happens? Well, when x is bigger than 1, x minus 1 is positive, so minus that is negative. This function is negative for x bigger than 1. And as this goes to 0, you're approaching minus infinity. On the other hand, if x is negative, x minus 1, sorry, if x is less than 1, x minus 1 is negative, minus 1 over a negative number is positive. The function is positive and going to plus infinity. So for this function, we can say the limit of f of x as x approaches 1 from the positive side is minus infinity, and the limit of f of x as x approaches 1 from the negative side is plus infinity. And the lines in both of these examples the vertical line x equal 1 is what is called an asymptote. So it's actually a vertical asymptote. So a vertical asymptote for a function is a vertical line at x equals c, where the limit of f of x approaches c from one side or the other side or both is plus infinity or minus infinity, either one or in any order. So that's what a vertical asymptote is. And a simple criterion for a vertical asymptote is the following. So this is a theorem. So if you have functions f and g continuous on an open interval containing the point C, so here's some number C, and there's some open interval around C on which the function is continuous, if f of C is not equal to 0, but g of C is equal to 0, then h of x equal f of x over g of x. As a vertical asymptote at the point x equals C. Because as x approaches C, f of x is approaching some non-zero number, but the denominator is going to infinity, is going to 0, so the function is going to plus or minus infinity. Any questions about this? So a standard exercise is given a function to find the vertical asymptotes. So this is example 2. We have first the function f of x equal 1 over 2x plus 1. So 1 is continuous, 2x plus 1 is 2x, 2 times x plus 1 is continuous. 2 times x plus 1, though, is 0 when x is negative 1. So there's going to be an asymptote at x equal negative 1. And the graph of this function this is 0. This is 1. This is going to be the vertical asymptote. Oops, sorry. Minus 1. So let me label this correctly. So this would be 0, minus 1, minus 2. And the asymptote is on this line, x equals minus 1. When x is bigger than minus 1, x plus 1 is positive. Function is going to plus infinity. When x is less than minus 1, this is negative. Function is going to minus infinity. So we have this vertical asymptote. Any questions about this? Okay. What about the function f of x equals x squared plus 1 over x squared minus 1? So this is defined when the denominator is not 0. That means for x not equal to plus or minus 1. And we can see a little bit more clearly what's going on if we factor the denominator, x minus 1, x plus 1. So this function is going to have vertical asymptotes. It's going to have 2 of them at x equal minus 1 and x equal plus 1. And the graph of this function going to look like this. This is the vertical line, x equal -1. This is the vertical line, x equal +1. And this, for example, when x is 0, f of 0 is -1. And when the numerator is always positive, x squared plus 1 is always positive. If x is between -1 and +1, x squared is less than 1, this denominator is negative. And this function is going to approach, the denominator is going to 0 as x approaches 1, but it's negative. So this function is going to look like this. It's going to -infinity as you approach plus or minus 1 from inside. And if x is bigger than 1 or less than -1, x squared is bigger than 1, so this is positive. Positive over positive is positive. Function is going to look like that. So as you approach -1 from the left, the limit is +infinity. As you approach -1 from the right, the limit is -infinity. Let me just write all these things down because it's useful to know. So for this function, the limit of f of x, as x approaches -1 from the left, is infinity. And the limit of f of x, as x approaches -1 from the right, is -infinity. The limit of f of x, as x approaches +1 from the left, is -infinity. And the limit of f of x, as x approaches 1 from the right, is +infinity. Okay. So our first example had one vertical asymptote. This example has two vertical asymptotes. Are there any questions about this? Okay. And the third part of this example is f of x equals the cotangent of x. Well, you have to remember the definition of the cotangent. It's sine of x over cosine x. And this has a vertical asymptote wherever the denominator is 0. Cosine x equals 0 at x equal to pi over 2, 3 pi over 2, 5 pi over 2, plus any multiple of pi, positive or negative. So this is 0, pi over 2, 3 pi over 2, 5 pi over 2, minus pi over 2, minus 3 pi over 2. These lines, whoops, I'm sorry. Let me do this example, but I wrote down not the code, it's the tangent of x. That's sine over cosine.
Oh, I'm going to say that.
Right? Is there a question?
Oh, I saw the error.
Yeah. So tangent of x, sine over cosine. The denominator is 0 at pi over 2 plus multiples of pi. So these vertical lines, these are all the vertical asymptotes. And the graph of the tangent looks like this. It's periodic with period pi, and these are all the vertical asymptotes. Now, suppose we have f of x equals x squared plus 2x minus 8 over x squared minus 4. Where are the vertical asymptotes? Well, this is only defined for x squared not equal to 4. Of course, you can't have the denominator 0, which is the same as x is not equal to 2 or negative 2. So you might think, well, they're vertical asymptotes at 2 and negative 2. But our theorem said you have a vertical asymptote at a point where the numerator is not 0 and the denominator is 0. And when x equals 2, the numerator is 4 plus 4 minus 8, 8 minus 0. So at x equal 2, the numerator is 0. So it's not like we know we have a vertical asymptote there. At negative 2, we have 4 minus 4 minus 8. That's okay. So we know there's a vertical asymptote at x equal negative 2. But what about x equal 2? So it turns out this function factors. We know the denominator factors x minus 2, x plus 2. And the numerator, I think, factors into x plus 4, x minus 2. You multiply this out, you get x squared plus 2x minus 4. And these cancel. So and when you cancel, you get x plus 4 over x plus 2. So here we see we have a function that has a vertical asymptote at negative 2. So this is the line x equal negative 2. And the graph of this function, let's see, when x is 0, it's equal to 2. And the graph of this function looks like this. And it's not defined at x equal 2. This function is not defined at x equals 2. But this is what's called a removable singularity. Because if we define the function to be equal to 2 at x equal 2, we'd have a continuous function. But what we're asking this problem is not about removable singularities, just where are the vertical asymptotes? And the important fact is that you have this vertical asymptote at negative 2, and oops, not sure. This should be 0, 2. And yeah. This is the point 2, 3 halves. This is the point 0, 2. So if you factor the numerator and denominator, you see this function is really equal to this, and this has a singularity, has a vertical asymptote at negative 2 only, just one. Okay, well, all of today's lesson is finding limits, and we'll do a few more, and then I'll do some of the homework problems, because it's actually a rather short lesson. Are there any questions so far? Any questions about this? So example 4 is to find first the limit as x approaches 1 from the left, the minus direction, x squared minus 3x over x minus 1. Now you can factor the numerator. This is x times x minus 3 over x minus 1, but there's still no cancellation. As you approach 1, the numerator goes to -2, it's non-zero, and the denominator is going to 0. So there's a vertical asymptote at x equal 1. When x is equal to 0, the value of the function is 0. When x is bigger than 1, let's see. Let's start with easier. If x is less than 1, the x minus 1 is negative. If x is less than 1, x minus 3 negative times negative, this is positive. If x is between 0 and 1, this is positive times negative. This is negative. I'm trying to find a nice way to understand this. So if x is bigger than 1, then x minus 1 is positive. If x is bigger than 1, but also less than 3, then x minus 3 is negative. So x times x minus 3 is negative. So when x is bigger than 1, this is a negative number over a positive number. It's negative. So this function is going to minus infinity. This is approaching this is going to 0, and this is approaching a limit. And on the other hand, if you approach x equal 1 from the left, what can we say? So if x is less than 1, then x minus 1 is negative. And if x is bigger than 0, then x minus 3, if x is less than 1, x minus 3, so x minus 1 is less than 0, x minus 3 is less than minus 2 is negative. And so what we have here is a positive times a negative number. A negative number times a negative number is positive. So this is positive, and the denominator is going to 0, and the function is going to infinity. So, so what this says is the limit of this function, x squared minus 3x over x minus 1, as x approaches 1 from the right is minus infinity. The limit as x approaches 1 from the left of x squared minus 3x over x minus 1 is plus infinity. What does the graph of this function really looks like? So let me do an experiment. So can you see this Maple worksheet? Is that visible? Can someone say yes or no?
Yeah, we can see it.
Okay. So we have this function, f. Well, let's just plot it. So let's say we want to plot this function, x squared minus 3 times x divided by x minus 1. Let's say we'll plot it from x going from -5 to 6, and y going from -20 to 20. Huh. So that's what the graph looks like. And you see, here we have this vertical asymptote at x equal 1. And that's what it looks like. You do it over a bigger range, it looks like that. So that's our function. Actually quite nice. Okay. Let me do a few more examples and then I'll do some homework problems. Maybe just for completeness, I'll mention some rules about limits at infinity, which are useful to know. So this is a theorem which says the following. Suppose we have functions f and g, and the limit of f of x as x approaches the number c is infinity, and the limit of g of x as x approaches c is some number L, which is not infinity, it's a real number L. So we have the following rules. The limit as x approaches c of f of x plus or minus g of x is infinity. This is going to infinity. This has a finite limit, and adding something finite to infinity is still infinity. If we take the product of these two functions, if L is positive, this is going to infinity times some positive number, which is infinity. But if L is negative, something going to plus infinity times something negative switches it to going to minus infinity. And the limit of g of x over x of x as x approaches c. This approaches a finite limit. The denominator is going to infinity. So this is 0. So this denominator is getting bigger and bigger and bigger. So for example, if you have the limit as x goes to 0 of 1 plus 1 over x squared, this is the sum of two functions. 1 has limit 1, that's just a constant. 1 over x squared as x goes to 0 is going to infinity. So that's this first rule. This is infinity. If we have the limit of x squared plus 1 over the cotangent of pi x, as x goes to 1 minus from the left, let's see, x squared plus 1 has a limit too. The cotangent is cosine over sine. As x goes to 1, cosine of pi is minus 1. But as x goes to 1, sine of pi x is approaching 0. This is the graph sine of pi x. As x approaches 1 from the left, this is positive. So this is a positive number going to 0. So cosine over this is going to infinity. And so limit of cotangent pi x as x goes to 1 from the left is the same as the limit as x goes to 1 from the left of cosine pi x over sine pi x. And this is positive going to 0, so this is infinity. So this is going to 2 over infinity, which is 0. Right? So this is actually something which requires a fair amount of work to become familiar with. Let me do one more example, and then I'll go to some homework problems. Suppose we want to find the limit of 3 times the log of x as x goes to 0 from the right. So what does the graph of y equal 3 log x look like? It's only defined for x positive, and it looks like this. It crosses the x-axis at 1. And as x goes to 0 from the right, this function is going to minus infinity. Looks like that. So here's a problem. This is actually number 9 in the homework. Find the limit as x approaches minus 3 from the left of the function 1 over x squared minus 9. And find the limit as x approaches 3 from the left of x squared over x minus 9. So I'll give you a couple of minutes to work on these yourself. Well, I just check the attendance, and then we'll take a look at them. Okay. I have Amin, Leonardo, Legrand, Lopez, Elijah Atkins, Gordon, Bello, Fletcher, Verdziuli, Isaiah Tillett, Lozano, Reyes, Beltran, Segura, Soto, Molinuevo, De La Cruz, Garcia Vega, Fahim, Conwell, Alcantara, Wiley, Wendogo, Yassine Al-Kafi, yeah. So if I didn't call your name, I didn't mark you present. All right, well, so what are these limits? This is the limit
Minus infinity.
1 over x minus 3, x plus 3. As x approaches negative 3, x minus 3 is going to minus 6. If x is less than negative 3, x plus 3 is going to be negative also. So this is negative times negative is plus infinity. Oops. I want to do this as it is in the text. This is x squared over x squared minus 9. This is just multiplying this by a positive number. So this is still going to be infinity. Well, I know everyone is supposed to be taking Math 155, and not everyone who teaches Math 155 uses Maple, but that's just.
Excuse me, Professor.
Yes.
Could you explain the number 9 again?
Okay. So.
Question. I know how you got the.
So 1 over x squared minus 9 is 1 over x minus 3 times x plus 3, right?
Yeah.
And we want to take the limit as x goes to minus 3, but from the left. Now, whether you approach -3 from the right or the left, x minus 3 is going to -6 as x approaches -3. So this is going to be negative. And if x is less than -3, then x plus 3 is less than 0, right?
Yeah.
So this is approaching, this is negative, and this is negative. So the product is positive, but the denominator is also going to 0. So if you have a positive number going to 0, that means you're approaching plus infinity. Sorry, you're approaching plus infinity.
Okay.
So let
What
me
number
go.
is the second problem?
What?
The number for the second problem. Like the first problem was number 9.
Oh, I think this is number 11.
Okay.
So let me take advantage of the fact that,
Professor, can you explain the number 11, please?
right, well, as x squared, so the limit, so x squared as x approaches -3 is 9, right? X squared is positive. This is positive. So you still have a positive number over a positive number, and the denominator is going to 0. So this is going to plus infinity. Let me try and show this on Maple. So we just had the function for number 9, 1 over, just one second. So let me plot the function 1 over x squared minus 9. Well, that's what it looks like. And here, x equal -3, this is the vertical asymptote at -3. And as you approach -3 from the left, the function is going to plus infinity. Okay? That's what's going on there. As you approach -3 from the right, you're going to minus infinity, and so on. What about in number 11? In number 11, we had x squared over x squared minus 9.
So the number 11, I think it's a whole number.
Sorry?
The number 11, the limit, I think it's 3 over 2, minus 3 over 2.
As x goes to -3, this is what the graph of the function looks like. Well, it can't, first of all, as x goes to -3, the denominator is going to 0. So, and the numerator is going to plus 9. So the limit is either plus infinity or minus infinity. And if you look at the graph of the function, you see as x approaches, this is the vertical line, -3. As you approach -3 from the left, you see the function going up to infinity. So that's what's going on in problem 11.
So it's 3 or -3?
Sorry?
It's -3, it's 3, it's not -3.
No, in problem 9 and in problem 11, you want the limit as x goes to -3.
Oh,
Here's -3. And as you approach -3, the function's going to infinity.
Oh, it's because you wrote it as +3. That's why.
Oh, well.
Yeah, that's what you did, Professor.
Oh, I'm sorry. Yeah. I'm just trying to take it from the book.
Thank you.
Yeah. Let me look at another couple of these problems. Let me try and pick a couple that aren't so obvious. So we have some problems where we want to find the vertical asymptotes. So number 19, h of x is x squared minus 2 over x squared minus x minus 2. Now, you have a vertical asymptote where the denominator is 0, but the numerator isn't. So we want to find out, when is this denominator 0? Well, that means solving the quadratic equation, but if you're lucky, this factors. And I think this factors into x minus 2 times x plus 1. X squared minus x minus 2, yeah. So x squared x minus 2, which is x minus 2 times x plus 1, this equals 0 at x equal negative 1 and 2. And at those points, the numerator is not 0 at x equal minus 1 and 2. When x is 1, this is minus 1. When x is 2, this is 4 minus 2, or 2. So we have vertical asymptotes at x equal negative 1 and 2. And for fun, let's actually have Maple graph this function for us. So let's plot the function x squared minus 2 divided by x squared minus x minus 2. Hey, voila, there it is. And you see here at x equal negative 1, you have a vertical asymptote. And here at x equal plus 2, you have a vertical asymptote. So with Maple, you can see very clearly what's going on. Let's do another example. So things that are not necessarily so obvious. Suppose we have, this is number 24, f of x equals minus 3x squared plus 12x minus 9 divided by x to the 4th minus 3x cubed minus x plus 3. So the vertical asymptotes are the places where the denominator is 0, but the numerator is not. So to find where the denominator is 0, we should try to factor the denominator. That's the first step. Let's see. X to the 4th minus 3x cubed minus x plus 3. I guess I could write this as x cubed times x minus 3 minus x minus 3. Right? So because if you expand this, you get x to the 4th minus 3x cubed minus x plus 3. And then I can factor the x minus 3 from this. This is x minus 3 times x cubed minus 1. And I can factor x cubed minus 1. That's x minus 1 times x squared plus x plus 1. And this doesn't factor anymore. So this is equal to 0 at x equal 1 and x equal to 3. So those are the only possible vertical asymptotes. And they're vertical asymptotes if the numerator at 1 is non-zero and if the numerator at 3 isn't 0. Let's just look at the numerator. The numerator is minus 3x squared plus 12x minus 9. I can simplify that by factoring out a minus 3. I get x squared minus 4x plus 3, which actually I think factors into x minus 1, x minus 3. Huh. So this function is really equal to minus 3 times x minus 1 times x minus 3 over this x minus 1 times x minus 3 times x squared plus x plus 1. And these cancel. So this function just turns out to be minus 3 over x squared plus x plus 1. And this function is never 0. So it looks like this function has no vertical asymptotes, because we were lucky enough to be able to factor the numerator and the denominator. So let me check the work by going back to Maple. So suppose I want to plot this function. Oops. Plot. In the numerator, I have minus 3 times x squared plus 12 times x minus 9 divided by x to the 4th minus 3 times x cubed minus x plus 3. And what I said is, if everything is correct, this function has no vertical asymptotes. And that's what the function looks like. No vertical asymptotes. This is not, here it just comes down, turns around, comes back up again. And it's always negative. Very pretty function. Let's see. That's our function. Let's see if Maple will simplify this. Oh, yeah. It got exactly what we got. If you simplify it by factoring Maple, this is a very good command in Maple if you're taking Math 175. It simplifies it and it gives you this. Yeah, that's what we're doing. Now, in the same homework in this section, there are also some problems from section 2.4, 49, 51, and so on. So the problem is to find the points of discontinuity. If any, and the ones which are removable, if they happen to be removable. So for example, in number 49, we have the function f of x is equal to x over x squared plus 1. Now in this function, x squared plus 1 is greater than 0 for all x. So this function is continuous everywhere. There are no discontinuities. Problem 51 is the function f of x equals x plus 2 over x squared minus 3x minus 10. Now, the denominator does factor into x plus 2 times x minus 5. So for x not equal to 2 or 5, this is the same as 1 over x minus 5. So this function is discontinuous at x equal negative 2 and x equal 5. Should be x equal negative 2. But at x equal negative 2, we have a removable discontinuity. If we define f in negative 2 to be equal to 1 over minus 2 minus 5 or minus 1 over 7, we remove the discontinuity. Let me do just one more and then we'll stop for the day. I don't want to do every single problem. Suppose we have number 57. The function f of x is defined in two ways. A half x plus 1 when x is less than or equal to 2, and 3 minus x when x is greater than 2. What does the graph of this function look like? When x is greater than 2, this is just a straight line with slope minus 1. When x is less than or equal to 2, this is a straight line. Oops, I didn't draw this properly. Let me draw this better. No, sorry, I drew it fine. That's exactly what it is. This is the point 2 comma 1. When x is less than or equal to 2, this is a straight line with slope a half. Looks like that. And you see that for this function, the limit of f of x as x approaches 2 from the left is equal to 2. The limit of f of x as x approaches 2 from the right is 1, and they're not equal. So we have a discontinuity at x equal 2, and there's no way you can define the function at 2, which makes this a continuous curve. So this discontinuity is not removable. Okay. All right. Are there any questions about anything we've done today? All right, well, we're halfway to the first exam. The first exam is lesson 13, and we've just done lesson 6. So 6 more lessons and then exam 1. So it looks kind of cold and snowy out. Hope everyone's able to stay warm. Be glad you don't live in Texas.
Wait, so Professor, quick question.
Yes, sir.
So the reason why it's not removable is because on the x-axis, it doesn't connect. Is that
Well, right.
correct?
So if you could remove it, there would be a way to define the function at 2. So this was a continuous curve. But since this is approaching 2 from the left and approaching 1 from the right, there's no number that will connect these, right? You can't draw a line. It has to be just one point. So this is a fundamentally not removable singularity. And let me do a similar example where you might have a removable singularity. So let's look at number 55. So here, the function f of x is equal to x if x is less than or equal to 1, and x squared if x is greater than 1. Well, actually, in this case, it's no problem because when x is less than or equal to 1, this is just the line y equals x. And when x is bigger than 1, it's the parabola. And they both meet at x equal 1. So there's no discontinuity at all. There's no, right. We just don't have to worry about that.
Oh, okay, I get it now.
Yeah. So even though they have different definitions for x less than 1 and x bigger than 1, they agree at this point, and there's no discontinuity. So it's not that it's a removable discontinuity. There's no discontinuity.
So, Professor, what will be the limit of 1?
Sorry, I didn't hear what you said.
So what will be the limit?
The limit? What? Well, I mean, if you ask what is the limit of f of x, sorry, this should have been a 1 here. The limit of f of x as x goes to 1 is 1. Because whether you approach from the left or from the right, you still approach 1 as x approaches 1. But it's a continuous function, so the limits are easy. Okay, well, are there any other questions? If not, then we're done for the day and be back on Wednesday. Bye, everyone.